Good morning to all of you. So, today we will talk about continuous probability distributions, and to begin the discussion I would like to summarize what we learnt in the last class. We discussed about discrete random variables, and in the context of discrete random variables you always talk about a set of some outcomes. So, I will talk about, for example, in the case of a dice which has 6 phases, then the set of outcomes is basically 1, 2, 3, 4, 5, 6. Okay. You have no more or no less than these 6 outcomes when you toss a die that has 6 phases. You could take a coin and write down this set of outcomes as head and tail. Okay. So, typically what this means is that the probability of having an outcome as 3 in the case of a die is basically 1 upon 6, because there are 6 phases and the die is unbiased. So, each phase has a probability of 1 by 6. Okay. And in the case of a coin, the probability of getting a head in a single toss is 1 by 2, because the coin is also unbiased. Okay. Now, before we proceed to the discussion of continuous probabilities, let me tell you a few important axioms related to, or axioms in the context of probability. Okay, so these are like facts stated without proof, and any notion of probability must satisfy this. Okay. So, the first axiom of probability is that the probability of any outcome, let us say E is the outcome, E could be the face of a die or the face of a coin, has to be always positive. So, probabilities are always positive, they cannot be negative. Okay. So, this is called as the positivity of probability. You cannot have probability of getting a head of a coin as negative. Okay. It has to be always positive. Second important axiom of probability is connected with events that are disconnected or independent. Suppose I ask you, what is the probability of getting a event E1 or E2? Okay. So, this is basically meaning that I am asking the question that what is the probability of having either E1 or E2, provided E1 and E2 are independent or disconnected. What this means is that suppose you ask me the simple question, you take E1 as head and you take E2 as tail, and you ask me in a coin toss, what is the probability of getting a head or a tail? The answer is 1, because you have only head or tails. So, you will say that probability of getting a head or a tail is nothing but the sum of these two probabilities, and that is 1, which means you will always get either a head or a tail. And of course, as I said, head and tails have to be disconnected events, okay, which is definitely the case here. The third important axiom of probability is that it is always normalized, which means if I have a set of events E1, E2 all the way to En, then these probabilities sum up to 1. Okay. So, this is a very important condition on probability, that your probability is normalized. So, this is called as the normalization condition on probabilities. So, if you have information to all the events, okay, then the sum of probabilities of all these events. In the case of coin tosses, I know probability of a head plus probability of a tail is equal to 1. So, for the coins you know this, and for the die you know the probability of 1 plus probability of 2 all the way to a probability of 6. This will add up to 1 for the okay. So, we have three important conditions here. One is the positivity of probability, that probability of any event has to be always positive, and if you have two events which are mutually disconnected or independent, then the question what is the probability of getting either E1 or E2 is nothing but the sum of these two probabilities. And the final question is, if you have a collectively exhaustive set of events, that you have no more than E1, E2 all the way to E1, En events, you have all the events, then a sum of probabilities of each of these adds up to 1. Okay. So, three important axioms connected with probability, discrete probabilities, are also seen to carry forward into the domain of continuous probability distributions, as we shall see. Right. So, now I just want to tell you a few important concepts regarding measurement of probability. So, how does one measure, probabilities of any event? Okay. So, this is the question, how do you measure? Well, there are two ways to measure probability of any event, and just by the difference in the nature in which they are measured, I call them objective method, okay, and a subjective method. I will give an example. What is this meaning of objective and subjective? Okay. So, suppose you take the example of the dice, 6-phase die, and suppose you ask me what is the probability of getting an outcome, let us say 4 in a die which has 6 phases. Well, I would say you toss the die n number of times, okay, and count how many times you get 4. So, n4 being the number of times you get the phase 4, and n being the total number of times you have tossed your die. Now, if n is large, that is if I take the n here to infinity, then the probability of the phase 4 coming up in a single toss becomes the right hand side. Okay. So, if you take n to be 1000 or 10,000, okay, so this would give you the probability of getting probability of getting a particular phase 4 out of n measurements. But you would also say that in the case of a die toss, since each phase is unbiased, you can argue that no experiment is needed, and I can simply say that the probability of getting a phase 4 is simply 1 by the total number of phases. Okay. So, in this case, for the particular case of a die toss, you could have answered the question subjectively without carrying out any experiment, because you knew exactly the number of faces and you knew the fact that the die is unbiased. So, the objective and subjective methods will lead to the same answer. You do not need to do it objectively, the subjective method suffices. So, I can simply say that the limit n tending to infinity, number of times you got the face 4 divided by n, basically tends to 1 by 6. Okay. So, both these methods will give you the same answer. In the particular case of a die toss, the subjective method suffices, but you shall also run across methods where situations where you may not know how to compute the probabilities subjectively. In that case, your only resort is to do it objectively, do a simulation perhaps, or do an experiment perhaps, and find out the probabilities objectively. Fine. So, now let us proceed to the discussion on continuous random variables. So, we will talk about continuous random variables now, and they are of great importance in statistical mechanics. So, I am going to spend a significant amount of time building the mathematics of continuous random variables. So, you could think of a set of random variables going from some a to b. Okay. So, your random variable x is in the set a to b. Okay. So, you can think of your x to be between a and b, and s of x is nothing but any outcome of a measurement of x. Okay. So, s of x basically refers to an outcome of measurement on x. So, if you measure x, you will always get s of x between a and b. That is the meaning of s of x. Okay. Now, I can take a to be minus infinity and b to be as plus infinity. So, the same s of x will become minus infinity to plus infinity. So, it is like here there was a bounded interval, but I am not restricted to these bounded intervals. I can take s of x to be unbounded. Okay. It is possible to have an outcome of measurement of x unbounded. For example, the velocity of gas particles in this room has a velocity distribution that is unbounded. It can have a theoretical probability, to have a it is possible to have a finite probability of finding a gas particle with very large velocities. It is only becoming 0 in the limit velocity is getting infinite. Okay. So, velocity distribution is one such example. What needs to be understood here is that, notice in the case of discrete probabilities, the normalization implied that your sum of all probabilities, xi being one of the n outcomes on x, this was 1. This was your normalization condition, that you had all the outcomes, n outcomes, and the probability of each outcome if added gives you 1. Okay. For continuous probabilities, or continuous probability or probability of a continuous random variable, this normalization condition reads as, of course, I cannot have a summation now because I have infinite number of measurements in any interval, either finite or bounded interval. I have to write down my normalization as some minus a to plus a p of x dx as 1, okay, because whether the interval is bounded. In this case, I have taken a bounded interval. Okay. So, my interval is basically minus a to plus a, Sx being a measurement of the random variable. Even though the interval is bounded, the random variable in principle can be anywhere in this interval. So, there are infinite real numbers that I can conceive of in this bounded interval minus a to plus a, which means I cannot work with the summation I worked in the discrete probability case. I have to work with an integral. Now, a direct consequence of this integral is that the probabilities in the second case have become dimensional. Okay. This is a very important point, that P, and I am going to use a different color just to alert the reader. The very first qualitative difference that our probabilities have picked, that they are now dimensional. So, when you go from discrete to continuous, the first thing that happens to a probability is that they become dimensional, and the dimensional dimensions here are 1 upon x. Okay. Because the right hand side is 1, which is dimensionless. So, probabilities are now dimensional, which means they are not really probabilities. They are not really probabilities. In fact, one should call them as probability densities. Okay. They are now called as probability density. So, this is an important difference that you must keep track of when you are discussing continuous variables. So, continuous random variables are described by probability density functions, not probability themselves. Okay. Only discrete random variables are specified by probabilities which are dimensionless. Okay. So, here I will say that P of x are dimensionless, they are just numbers, pure numbers. In the case of continuous probabilities, P of x are probability densities. Okay. So, how does one construct probability densities? So, how do you, that is the next question that comes to my mind. Okay. So, if I am going from discrete probabilities which are purely numbers, how do I compute probability density functions? Or commonly referred to as PDFs. Okay. So, that is the next topic. So, to construct PDFs, you need a notion of a cumulative probability function. So, this needs a notion of a cumulative probability function, also called as CPF, and I shall define what is the CPF. So, you take off this capital P of x as a cumulative probability function, and this P of x is nothing but is the probability of getting a measurement x in the range minus infinity to x. Okay. Suppose my x varies between minus infinity to infinity, and P of x, this capital P of x simply tells me if x belongs to minus infinity to plus infinity. So, P of x is simply a probability of getting a measurement on x between minus infinity to x. So, let us sketch this schematically. So, this will go to plus infinity and this will go to minus infinity, and if I am plotting the cumulative probability function, then I know at minus infinity the probability of getting an x is 0, okay, because that is just one point, and as you increase x, this value will slowly cross the y axis, at which point you will say the cumulative probability function is half, and then as you go towards the positive infinity, so let me just do this properly. It will saturate to 1. Okay. It will saturate to 1. So, this point would be 1 and this point will be half, and this is the origin 0. Now, it has to be half at origin, because if x is a random variable between minus infinity to plus infinity, the probability of getting an x between minus infinity and 0 should be half, because that is precisely the half range of x. Okay. If x is between minus infinity and plus infinity, the question what is the probability of getting an x between minus infinity and 0 is half, because this is precisely where half of your measurements are. And naturally the question, the answer to the question what is the probability to find an x between minus infinity to plus infinity, the answer is 1, because you always find an x on the x axis, and so the CPF is 1 as x goes to infinity. So that is the definition of CPF. Then you can construct the probability density function p of x as simply the derivative of the cumulative probability function. So, this is the definition of probability density function. So, if you want to know what is the probability density around some point, let us say at this point, this is the x, you simply compute the derivative here, call that d by dx of p of x, and this is nothing but the probability density at point x. Okay. So, that is basically the measurement, that is basically the way you construct a probability density function, knowing the cumulative probability function. So, this is one way to construct PDFs. Let us now proceed to some examples where you will encounter in statistical mechanics. So, some examples of PDFs that you see in physics, I will just bring up two simple examples, and you can refer to the upcoming tutorial for more important examples. So, I will just give you two examples of two commonly found examples of PDFs. So, one is a step distribution, step probability density function. So, this is like saying that the probability of finding an observation between minus a to plus a is constant, is uniform. Okay. So, it is a flat distribution function. If I ask what is the probability of getting at this point, well, the probability is this, which is 1 upon 2a. This point on the x axis is 1 upon 2a. It has to be 1 upon 2a. Why? Because if I normalize my PDF, okay, between minus a to plus a, that is the range of my PDF, I must get 1, okay. And since p of x is constant, So, it can come out of the integral. Integral dx between a and minus a is simply twice a, the right hand side is 1. So, this will give you 1 upon 2a. Okay. Okay. So, this is one example of a PDF, that any measurement that you take on the x axis between minus a and plus a, the probability density is 1 upon 2a. So, this is also called as a flat distribution. Okay. So, all measurements between minus a and plus a are equally likely. Okay. So, all measurements x between minus a and plus a are equally likely. You can also take some non-uniform distributions. Since I have given the example of a uniform distribution, I am also giving you some important non-uniform distributions. Okay. So, one distribution that you have probably heard already in statistical in your prior encounter with some kinetic theory is a velocity distribution which is Gaussian. So, I will take a one dimensional Gaussian distribution. Now, this distribution is the domain of the independent variable is unbounded, also called as a bell curve. Okay. So, your x will go from minus infinity to plus infinity. Okay. And this PDF here is maximum at x equals to 0. Okay. And this PDF has a functional form of some normalization constant that will be made clear later into e raised to minus x square. So, this distribution function falls on both sides of the y axis, and the normalization constant is basically this is basically a factor that normalizes the Gaussian PDS, the Gaussian PDF, meaning that I can calculate what is my n0 by simply integrating my PDF and demanding that this be equal to 1. This will give me n0. Okay. We shall do this later on and find out what is precisely the value of this n0. But for the purpose of this discussion, it is not necessary to compute it. Now, just compare this distribution with the previous distribution. Here, it is more likely to find an observation of x close to the origin. So, this region is more likely than maybe this region. And the simple reason is the probability densities are much smaller here compared to the probability density around origin. So, most of your measurements will be sitting near the origin where p of x is maximum. Okay. And as you go far away on either side of the x axis from the origin, you see that the PDFs become smaller and smaller, which only means that if you take a measurement on x, it is likely to be situated near origin. Okay. For example, if x was nothing but the x component of velocity of particles in this room, then if you take a measurement on the x component of velocities of particles in this room, you will find that it is more likely to find a particle with 0 x component of velocity, which means it just says that the average x component of velocity in this room would be 0, and so will be the y component, and so will be the z component. And that is because the particles in this room do not have a drifting center of mass movement. Okay. So, we have two different types of probabilities here, flat probability distributions and non-uniform probability distributions, and we will discuss several such distributions in the upcoming lectures. And in the tutorial we will discuss how to go from a flat distribution to a non-uniform distribution. My TAs will discuss through the aid of some problems, and it shall become more clear how do we do this. Okay. So, now I am going to basically describe one very important method of mapping one distribution to another. So, I am going to partly answer the previous question, leaving some room for discussions to the assignments that is coming up. Okay. But I will discuss some theoretical steps, and one example I will discuss in this class just to aid the understanding. Now, suppose you have a continuous random variable x, okay, and the PDF of this random variable is p of x. Okay. So, p of x is the PDF. Okay. X is a random variable, p of x is the PDF. Now, suppose, so let me just define, let us take some example of this PDF, okay, before we complete the question. So, let us say this PDF is exponential. Okay. So, say p of x is e raised to minus x, okay, and e raised to minus x is a PDF, a valid PDF that goes as an exponential. This point is 1, this is 0, you have infinity. Okay. And if you want to check that p of x is a valid PDF, you can compute its norm. Okay. So, you take the range 0 to infinity, and this will come out to be minus e raised to minus x in the range 0 to infinity, which will be 1. So, this is a properly well behaved probability density function. Okay. So, the norm is 1. So, now my question is, if p of x is e raised to minus x and that is given to you, you consider another random variable, and this is my question. Okay. So, please pay attention here. So, consider a new random variable, a continuous random variable, let us say it is y, and this y has a relationship with x. Let us say this relationship is quadratic, y is x square. What is the PDF of y? Meaning, let us say the PDF of y is p of y, and this is a function of y. What is this p of y as a function of y? Okay. That is my question. So, the answer to this question is basically relies on conservation of norm. Okay, or conservation of the normalization conditions. So, for each measurement of y, each measurement of x, if there is a unique measurement of y, by the way this measurement need not be unique, the function y could be non-monotonous, but as long as you account for all the measurements on y appropriately, then you can write down this condition that p of x dx, which is nothing but the probability of getting a measurement x in the interval x to x plus dx, okay, is the same as PDF Py of y dy. So, this PDF of y is called as P of y. The subscript here is only to indicate that we are looking at the PDF of y, okay. That is what the subscript here indicates. So, this is basically saying that it is the same as the probability of getting y in the neighborhood of y plus dy, okay. So, basically what we want to say is that whether you measure x and compute px dx, it is the same as p of y dy, okay, and we want to chase this probability density, knowing the probability density of x and the relationship y equals to x square. Okay. So, this is what we have in our hand. So, you can actually write down this equation 1 as p of y equals to p of x dx by dy, okay, where this quantity dx by dy is called as the Jacobian of the transformation. So, I am transforming the probability on x to the probabilities on y, and this transformation is affected by a Jacobian. Please note that I have kept a mod sign for the Jacobian because I can't have a negative Jacobian. And so, one can compute the left hand side by computing the derivative dx by dy. So, you can take this, I will call this as maybe 1a, okay, and you can take the derivative d by dy of equation 1a, okay, and what you get? You get 1 as twice x dx by dy, okay, which basically means that dx by dy is 1 upon 2x, okay. So, if you plug dx by dy in equation 2, what do we get? We get the PDF of y, which is a function of y, as PDF of x into mod of 1 upon 2x, because that is what is the dx by dy, which is nothing but 1 upon 2 into p of x into 1 upon mod x, okay. Now, recall that our relationship between y and x was a simple quadratic relationship. So, y was x square, which means that I can write x as plus or minus square root of y, but here I need mod x. Okay. So, I can write this as 1 upon 2 p of x into 1 upon square root of y, because it does not matter whether you take plus or minus, mod of plus or minus is always plus, and our original PDF was exponential. So, I am simply writing for p of x as e raised to minus of x, and x is square root of y divided by square root of y. Now, I cannot take minus x here for the simple reason that my PDF is not defined, since x is, if you look our original PDF, it is defined only for positive x. Okay. So, I will not take the negative values here, because px defined only for positive x. Okay. So, I cannot take a negative square root of y here in the numerator. Okay. You can write down here that p of x defined only for x greater than 0. So, you can't take p of you can't take a negative x in the definition of p of x. Okay. So, with that, this definition of p of y emerges. So, I can write down the distribution of y that I was chasing as e raised to minus square root of y upon twice of square root of y. Recall that our original distribution on x was e raised to minus x. So, if your original distribution was e raised to minus x and your x and y are related by this expression, then this is the final form for the distribution of y, and we have used the method of Jacobians to map one distribution into another. Okay. So, let us plot this distribution also. So, our new distribution is basically, this is my p of y as a function of y. It has to be like this. At y equals to 0, this will blow up because there is a square root of y singularity here, but that is not to be, that does not pose any concern to me, because this singularity is integrable. I will explain what is the meaning of this integrable singularity. Let me first sketch this function here. Okay. And our p of x is the old function. This is 1, 0. Okay. So, this PDF that we obtained for y is also normalized, and this is because this singularity at y equal to 0 is integrable. So, you check if these are the checks you must perform, is normalized, otherwise it is not a proper PDF. Okay. So, this check can be done by simply integrating this function in the domain of y. So, I will take this function and integrate in the domain of y. Domain of y is 0 to infinity, and you can write this as 0 to infinity. The form of p of y is e raised to minus square root y upon twice of square root y dy. Okay. The singularity at y equal to 0 poses no issue, and that can be seen by simply making a substitution of square root of y as some variable u, thereby giving me 1 upon twice square root of y dy as d of u. Okay. and the limits y going from 0 to infinity are now transformed to my limits on u as 0 to infinity, limits do not change. So, my integral becomes 0 to infinity e raised to minus u du, which is nothing but minus e raised to minus u in the limits 0 to infinity, which is nothing but 1. So, as you can see, the singularity was integrable and my PDF on y is also well behaved. So, you can, the take home conclusion is that P of y is well behaved. Okay. So, that is how you map one distribution into another through the method of Jacobians. And once you do this mapping, please check that your distribution is well behaved. It has all the axioms, it is obeying all the axioms that we discussed in the context of probabilities, that it is positive, it is norm conserving. These are the two properties that you should always check. Okay. So, we come to an end here, and in the next class we will maybe discuss one or two more examples and proceed towards the computation of characteristic functions, which is a very important method of computing moments or averages in any distribution. So, we will take it up from there in the next class.